Colligative properties are kind of interesting because they depend only on the amount of stuff dissolved in your solution, not what type of stuff is dissolved. So it doesn't matter what solute particles are present, just that they are. And that the value of the property depends on the concentration, so how much solute is dissolved into the solution. And the main reason for this has to do with the fact that these solute particles are actually blocking the solvent at the surface. So it has a lot to do with the attractive forces and the solute particles occupying spots that the solvent normally would. So we've got our extra solute particles in our solution. Vapor pressure is an example of a colligative property. So if we have solute particles that are blocking positions at the surface, the vapor pressure of our solution is going to be lower than the vapor pressure of just solvent all by itself. So our solute particles replace some of the positions, making it harder for the solvent to escape the surface. So this has some interesting consequences. So one of those consequences is that if we put pure solvent and a solution in a closed system, that solution will actually draw particles into the solution, and the level of the pure solvent will decrease in volume, and the solution will actually increase in volume. So it draws those pure solvent vapor into that mixture because of its tendency to mix. So beakers that start with equal levels will change over time. This change in vapor pressure also affects our freezing point and our boiling point. So the vapor pressure lowering occurs at all temperatures, and this results in the temperature required to boil the solution being higher. So we actually increase the boiling point if we add solute into our pure solution. So this is part of the reason why you add antifreeze into your car's radiator, because we're trying to increase the boiling point of the water so that it can cool your car more effectively. It also results in the temperature required to freeze the solution being lower than the freezing point of the pure solvent. So it actually decreases our freezing point. So essentially what is happening is we're spreading out the liquid range on our phase diagram. So we are a liquid longer. So it increases the boiling point and it decreases the freezing point. And this decrease in freezing point is why we add salt to sidewalks in the winter to eliminate or to decrease the freezing point of water so that the ice will melt. So let's look at freezing point depression. We can calculate the decrease in the freezing point based on the concentration. And it is a decrease. So we're going to take the freezing point of our pure solvent and subtract the freezing point of our solution, and that gives us the change in temperature of the freezing point. Now, it is determined, or it's related to the molality, so little m. So molality, remember, is moles of solute over kilograms of solvent. Okay. And there's a proportionality constant called the freezing point depression constant, or KF. It depends on the type of solvent we have, but not the solute that's added. And those units are degrees Celsius per molal. So depending on the type of solvent that we're using, we're going to have different KF values, and when we get to boiling point, we also have different KB values. So that KB is the boiling point elevation constant. Because we're looking at a change from the normal freezing point or boiling point, we do need to know what those freezing point and boiling point are of the pure solvent. So frequently we'll be using water. So 0 degrees is our freezing point, 100 degrees is our boiling point. But if we do use different solutions or different solvents, we can look up the normal boiling point and freezing point. Let's calculate the freezing point of a 1.7 molal, lowercase m, aqueous solution. So aqueous means we're dissolved in water of ethylene glycol. So we are going to need the KF of water, and the KF for water is 1.86 degrees Celsius per molal. We can use our equation, our change in temperature of the freezing point is equal to the molality times our KF. So we're given molality. The KF is a constant. Our molality is going to cancel, and we end up with degrees Celsius. So 3.2 degrees Celsius is our change in temperature of the freezing point. So now freezing point is always depressed, so it's always lower. If we want to calculate our freezing point, it's going to be equal to the normal freezing point of water minus that change in the freezing point. So our freezing point is going to be negative 3.2 degrees Celsius because it's going to be lower than our original freezing point. Here's a practice for you to try. Pause the video and see if you can calculate the freezing point of a 2.6 molal aqueous sucrose solution. So our solution is aqueous, which means we're dealing with water again. So our change in temperature of the freezing point is equal to the molality times KF. Our molality is 2.6 molal times, for water, our constant is 1.86 degrees Celsius per molal. This gives us a change in freezing point of 4.8 degrees Celsius. We're limited to 2 significant figures because of our molality. So our change in temperature of the freezing point is the freezing point of the solvent, pure water, minus the freezing point of the solution. And we know we just calculated that it's 4.8 degrees Celsius. So our solvent is 0.0 degrees Celsius minus the freezing point of the solution, which equals 4.8 degrees Celsius. So our freezing point of the solution is negative 4.8 degrees Celsius. Again, it should be negative because it's a depression. It's a decrease in the freezing point. Boiling point actually elevates. So we're increasing the boiling point. And so the way that we're calculating our change in temperature reverses because our new boiling point is going to be higher than that of the pure solvent. And the equation looks very similar. Molality times a constant, which in this case is our boiling point elevation constant. It still depends on the type of solvent that we're using, and the units are the same as what we saw for the freezing point depression constant. So let's try an example. What mass of ethylene glycol in grams must be added to 1 kilogram of water to produce a solution that boils at 105 degrees Celsius? So we need to find our change in temperature. So our change in temperature is, our solution is 105 degrees Celsius. Pure water is 100 degrees Celsius, and so our change is 5 degrees Celsius higher. So if we want to take and find our change in temperature is equal to our molality times Kb. Kb is a constant for water. We know our change in temperature. We know the constant, so we can solve for our molality. So 5 degrees Celsius, the Kb for water is 0.512 degrees Celsius per molal. And so our molality is 9.77 molal. Now, we want to figure out how much ethylene glycol we need to add. So we're told that we have 1 kilogram of water. Our molality is kilograms of water over moles of solute, or moles of solute over kilograms of water. So we know that it's moles of our ethylene glycol. We can calculate the molar mass. Which is 62.07 grams for 1 mole. And so that gives us that we need 610 grams of our ethylene glycol per 1 kilogram of water in order to change the boiling point by 5 degrees. See if you can calculate the boiling point of a 3.6 molal aqueous sucrose solution. Change in the temperature of the boiling point is the molality times Kb. Our molality is 3.60. The Kb is our constant, 0.512 degrees Celsius per molal. So our change in temperature is 1.84 degrees Celsius. So our boiling point of the solution minus the boiling point of the solvent is equal to 84. And so our solvent has a boiling point of 100. So if we add that to the other side, the boiling point of our sugar solution is going to be 101.84 degrees Celsius. So we've increased our boiling point. The boiling point always elevates.